When you're on a flight, maybe staring out the window from seat 12A, have you ever actually stopped to wonder, why are all those windows oval? Always curved, never square.
It seems like such a small thing, doesn't it? Just a minor design choice.
Yeah, but there's a huge, a really critical engineering lesson hiding right there in plain sight.
There is. And for you, the learner who wants to get right to the heart of it, that's what this deep dive is all about. It's a story that actually connects high-altitude physics, simple geometry, and a pretty tragic history.
Okay, so to set the stage for this, we first have to understand why modern jets fly so incredibly high. We're talking 35,000 feet, sometimes more.
Right. And there are really two main reasons for that. First, the air is just so much thinner up there.
So less drag on the plane.
A lot less drag,
Hmm.
which saves an enormous amount of fuel. And the second reason is you're flying above most of the weather, the turbulence.
For a much smoother flight.
Much smoother, more comfortable flight.
Exactly. But flying that high creates a massive challenge for the structure, right? I mean, humans can't breathe up there.
No, you can't. So the cabin, it absolutely must be pressurized to keep a survivable atmosphere inside.
You're basically flying inside a sealed can.
A sealed can that has to withstand all of that internal pressure pushing outwards, which is why planes are cylinders.
A tube shape.
Yeah, a cylinder is just uniquely good at distributing that internal pressure evenly. It's like a balloon or a submarine. The shape itself eliminates weak points.
Okay, so let's unpack this then. If the cylinder is so strong and the pressure is even, how does cutting a small hole in it, a window, suddenly become a fatal flaw?
It all comes down to the pressure difference and what we call mechanical stress. When you're at cruising altitude, the pressure inside is much, much higher than the pressure outside.
Okay.
And that difference causes the skin of the airplane to expand, just slightly. The entire structure is under immense stress.
Like you're constantly stretching a giant rubber band.
That's a perfect analogy. Now, what happens when you cut a hole in that stretched rubber band?
It's a weak point.
It's a weak point, and this is where stress concentration comes in. Normally, that stress, that tension, flows smoothly through the material. But an obstacle like a window forces that flow of energy to bend and go around it.
And if that obstacle has sharp corners.
That's where all the trouble starts. To visualize it, think of the stress flowing like water in a river.
Okay.
An oval shape lets the water glide smoothly around it. But a square corner is like a sharp 90-degree rock wall.
The water would just slam right into it.
It slams into it, and all that force builds up. It concentrates right on that single point, the corner.
It's incredible that a few millimeters of a curve can make that much of a difference. And this wasn't just a theory. This was a fatal design flaw.
It was. This exact geometric mistake is what caused cracks to form on the de Havilland Comet.
The very first commercial jetliner.
The first one.
Yeah.
It was a revolutionary aircraft, but its square windows were its undoing. There were 3 catastrophic crashes in quick succession in 1953 and 1954.
And the investigation revealed it wasn't bad parts or shoddy work.
No, it was pure, unforgiving physics. The stress concentrating those sharp corners created cracks that led to explosive decompression.
The corners were literally ticking time bombs.
They were. And that hard-won knowledge is why every single commercial aircraft window you see today is oval or has rounded corners.
So the big takeaway here is that the next time you're flying, you're not just looking out of an oval window.
Not at all.
You're looking out of 70 years of engineering lessons that were learned from absolute catastrophe. That simple curve was the critical weakness.
It was. And if we connect this to the bigger picture, it really makes you think about all the other seemingly simple designs around you.
How so?
Well, how many are actually protecting you based on complex lessons learned from some past failure?
Things we just take for granted every single day.
Exactly. What small, perfected design choice, refined over decades of painful trial and error, do you rely on without even giving it a second thought?